Hi friends, today we will be dealing about the Hermitian operators. So in quantum mechanics, the Hermitian operators has got a lot of meaning. Why we are specifying that the operators in quantum mechanics should be Hermitian operators. The mere word that it should be a Hermitian operator implies that the values obtaining, the observables should be real values. So, if you are specifying that quantum mechanical operators are Hermitian operators, it means that the value that you are going to obtain by operating a Hermitian operator on a wave function will be real values. Let us move to the how we can write the equation for the Hermitian operator. So, it implies that integral psi star alpha psi d2, the volume element, should be equal to integral psi alpha star psi star d2. This is one way of stating the Hermitian property. In another way, we can write it as integral psi 1 alpha psi 1 star alpha psi 2 d2 equals integral psi 2 alpha star psi 1 star d2. So what does this equation means? This equation states that the resultants, the observables that we are getting from a operating from a equation like this, it should be real values. Actually, we know another, actually it comes in the third postulate. The third postulate says that alpha psi equals a psi, which is called as the Eigenvalue Equation. The Eigenvalue Equation states alpha psi equals a psi. So when alpha is the operator, psi is the wave function, and a is the eigenvalue. This eigenvalue should be real values. That is what the Hermitian operator says. So actually you see once again coming to this equation, this is alpha psi. So alpha is an operator operating upon a wave function psi, and you are multiplying it by a complex conjugate. It should be equal to, what it should be equal to, you are taking the complex conjugate of alpha. Complex conjugate of alpha is alpha star, and you are operating that with the psi wave function. That also is the complex conjugate. If these are equals, if the LHS, right hand side, is equal to left hand side, it means that the wave function, the resultant you are obtaining, the eigenvalue you are obtaining from it will be a real value. So that means this should be a real value. So always you have to select your operators such that the wave functions, the result values you are obtaining from it will be real values. That is what we call by the, or what, that is the definition of the Hermitian operators. So as you know, the second postulate states that the quantum mechanic corresponding to any observables, there should be a quantum mechanical operator, and that operator should be a Hermitian operator. So that is about the Hermitian operators. Now let us prove the Hermitian condition. So what was the Hermitian condition? We were saying that any physically observable after getting from operating by a Hermitian operator should be real operator. So we have the Hermitian condition, we have written the Hermitian condition here, and the psi is your wave function, which is an eigen function. Now alpha is the Hermitian operator. So it states that if psi is an eigen function for the Hermitian operator alpha, the value obtained from the physically observable value obtained, it should be real. To prove that, let us take an eigenvalue equation, which is going to take alpha psi equals a psi. Now I am going to take the psi star, the complex conjugate, I am going to integrate it. That means I am going to multiply by psi star alpha psi d tau should be equal to, again in this side also I have to multiply and integrate psi star a psi d tau. We know this will be equal to a integral psi star psi d tau. This is one equation. Now what I am going to do is I am going to take the complex conjugate of this particular equation. I am going to take the complex conjugate. So what will be the complex conjugate of this equation? It will be alpha star psi star should be equal to a star psi star. Now I am going to multiply by psi and I am going to integrate it. That means I am going to have the wave function psi and I am going to integrate. So it will be psi alpha star psi star d tau, which will be equal to integral psi a star psi star d tau. Of course, you know, here we can write it as a star integral psi psi star d tau. Now what is the Hermitian condition? Hermitian condition we have written here, psi star alpha psi d tau is equal to psi alpha star psi star d tau, meaning to say that this particular equation at this side and also this side are equal. If they are equal, we can easily equate these two. So what will be that one? This will be a integral psi star psi d tau should be equal to integral a star psi psi star d tau. It is easily understandable that these integrals are equal because both are integral psi psi star d tau. Even if we apply the normalization condition also, it will become easy. So that equal, that means a is equal to a star, which means that this a is a real value. So what does that mean? If we are operating a wave function using a Hermitian operator, the value, the physically observable, the resultant you are obtaining from that particular equation will be a real value. That means you can use Hermitian operators. You can use your Hermitian operators to determine the real values from a quantum mechanical system. So that is the proof that if you are using a Hermitian operator, you will be obtaining real values.